Sound can be described as the brain's interpretation of a physical stimulus in the form of a pressure wave arriving at the ear. Have you ever asked the question, if a tree falls in the forest, does it make a sound? The scientific definition would indicate it does. Philosophically, it is still up for debate. The point is, we listen using our brains. The reception of the physical stimuli by the human ear is a critical part of the nature of sound. A sound, or sound pressure wave, has three distinct elements: generation, propagation, and reception. Generation is the act of creating sound pressure waves by moving air particles. Propagation is the actual travel between the source or generator and the person who hears it. The last element is the receiver. That is, a human ear and the interpretation by the brain. When sound is generated, vibrations move through the air, propagating away from the source. A sound wave propagates through a medium via a series of alternating compression-rarefaction cycles. The sound source, or the origin of the pressure wave or sound, begins a chain reaction which causes nearby molecules. The human ear is capable of detecting the frequencies between 20 and 20,000 Hertz, or 20 kilohertz. The speed of sound is the rate at which sound waves propagate. We call this rate velocity. As a base unit, we will use 1130 feet per second as the speed of sound. The length of a sound pressure wave is known as its wavelength. Wavelength is the distance covered in one cycle. Wavelength is calculated by dividing the velocity by the frequency. The distance above or below the center line of a sine wave to the peak and valley is the amplitude. A waveform has both positive and negative amplitude. We interpret amplitude as the level or volume of the signal. Signal path is the route an audio signal. Phase describes the time travels from the input to the output of a system, learning how to trade between multiple signals and how they affect one another. When waves are in phase, their amplitudes are combined, creating a greater amplitude comprised of several parts, each with a specific function. Hearing starts with the outer ear. When a sound is made outside the outer ear, the sound waves or vibrations travel down the ear canal and strike the eardrum. The eardrum vibrates. These vibrations are then passed to three tiny bones in the middle ear called the ossicles: the hammer, anvil, and stirrup. The ossicles amplify the sound and send the sound waves to the inner ear and into the fluid-filled hearing organ, the cochlea. Once the sound waves reach the inner ear, they are converted by tiny hairs into electrical impulses, which the auditory nerve sends to the brain. The brain then translates these electrical impulses as sound. The brain is the key component when it comes to listening. We listen with our brain, not our ears. The ear is the transducer that converts the acoustical sound pressure wave into an electrical impulse the brain interprets. The ear is a nonlinear transducer. This means that it has a varying level of sensitivity to loudness based on frequency. The Fletcher-Munson equal loudness contour curves indicate the ear's sensitivity to varying frequencies at different loudness levels. For example, if a 500 Hz tone is played at 110 dB, a 100 Hz tone would have to be played 6 dB louder, and a 1000 Hz tone would have to be 3 dB louder to be perceived as the same volume. The ear is most sensitive between the frequencies of 1 kHz and 4 kHz, which coincidentally happens to be the frequency range at which a baby cries. Perception of loudness is how loud in volume a sound appears to be. This is important because a sound's apparent volume and its actual power or energy are not always the same. The ears and brain work together to estimate the distance of a sound source. The overall level of a sound, the time arrival, the timbre of the sound, and the ratio of direct to reflected sound within a space are the elements required for the brain to perceive the distance of the sound source. Auditory cues for the perception of the size of a space include sound intensity or loudness, frequency, and time arrival. The brain measures differences in time, energy, and frequency between direct sound and the early and late reflections of the sound to distinguish size. Spatial localization is the ability to perceive the location of a sound source. The brain uses two separate cues to determine the location of a sound source. These cues are the time and intensity difference between the two ears. When sound reaches one ear, it has greater intensity than when it reaches the other ear. This is because the sound pressure waves must travel around the head, losing energy in the process. This loss of intensity and time arrival differential allows the brain to recognize the location of the sound source. Surround sound manipulates the way the brain perceives direction, distance, and space. The brain locks onto what it hears first, not necessarily the loudest. Sound pressure level, commonly known as SPL, is how we quantify the level or amplitude of a sound pressure wave. It is expressed in decibels or dB. 3 decibel level thresholds to keep in mind are the threshold of hearing, feeling, and pain. The threshold of hearing is the level an average person can hear a specific frequency about half of the time. This level is noted to be 0 dB SPL, or 0 decibels. The threshold of feeling is approximately 118 dB SPL. The threshold of feeling is considered to be the level where most listeners experience discomfort about half of the time. The threshold of pain is approximately 140 dB SPL. This level will cause pain for most listeners. The first step to understanding sound and sound reinforcement systems is grasping the basic fundamentals of sound. The definition of sound, the elements of a sound pressure wave, the anatomy of the ear, and the interpretation by the brain are the first building blocks you must understand and learn. When you understand the fundamental elements of sound, you will begin to better understand why things sound the way they sound. Remember, we listen with our brain. Think about what you are hearing. This is where it all begins and ends. Signal path is the route an audio signal travels from the input to the output of a system. Learning how to trace and control this path is critical to understanding the operation of any audio system. An audio system schematic is a signal map that illustrates the route a signal will travel. There are three main sections the schematic can be divided into: input, routing and processing, and output. The input section includes devices that convert acoustic energy or recorded material into an electrical audio signal. The routing and processing section is composed of preamplifiers, mixing consoles, signal processors, and power amplifiers. The output section consists primarily of transducers, that is, loudspeakers, that convert the audio signal into acoustical energy. The signal path begins when acoustical energy is converted into electrical energy upon entering the audio system. It remains an electrical signal throughout the audio system. When the signal exits the audio system, it is converted back into acoustical energy and transmitted to the receiver. An audio signal path can be compared to a chain. Like a chain, an audio system is comprised of many links connected together to form a whole. The output from one link connects to the input of another. If one of the devices in the path falters, then the signal path will fail. Let's trace the signal path from a microphone, through the mixing console and processing equipment, to the loudspeaker and the listener's ear. The starting point in the audio system is the input device. This device can be a microphone or a line-level device, such as an instrument, a wireless microphone receiver, a tape deck, CD player, or audio from a DVD or VCR. The output of the device is connected to the input of a routing device, typically a mixing console. The output of the mixing console is connected to a processing device, such as an equalizer, compressor, crossover, or digital signal processor. Digital technology has paved the way to perform most all signal processing within one device, the digital signal processor or DSP. A DSP has the potential to provide multiple processing functions, including equalization, compression, limiting, frequency crossover, and signal delay on multiple channels simultaneously. The output of the processor is connected to a power amplifier, where the signal level is increased to a loudspeaker voltage level. The output of the power amplifier is sent to a loudspeaker or series of loudspeakers, where the signal is converted into an acoustical sound pressure wave. The loudspeaker is an output device of the audio system. Within the signal path, different voltage levels are present. The three most common voltage levels are microphone, line, and loudspeaker. Microphone or mic level is a very low voltage which requires amplification before it can be routed or processed. Thus, a microphone preamplifier must be used to elevate a mic level signal to a line level signal. The voltage level throughout the signal path within such devices as the mixer and the DSP to the input of the power amplifier is line level. Loudspeaker level is a high voltage level produced by power amplifiers to drive a loudspeaker. The voltage range depends on the power amplifier's rated output. It is imperative to match a device's input and output levels correctly. For example, plugging a power amplifier's output at loudspeaker level into a mixer's microphone input designed for mic level could cause extreme damage. Mismatching signal levels can be dangerous. Care should be taken to always match voltage levels, mic level output to mic level input, line level output to line level input, and loudspeaker level output to a loudspeaker's input. A signal can take multiple paths through the audio system depending on the routing devices and configuration. Let's review a system with 4 inputs and multiple signal paths. The first input signal is routed through the mixer to the processing unit, then to the power amplifier and loudspeaker. The signal could be routed simultaneously to a pair of headphones and through an auxiliary bus to a separate processor, power amplifier, and loudspeaker. The second input device is routed through the mixer like input 1, but is also routed to a tape deck for recording purposes. The third and fourth inputs are routed like input number 1, but are sent to multiple loudspeakers by way of the digital signal processor. As you can see, a single input source can be routed to a number of outputs by taking multiple paths. With the addition of more input sources, it is easy to see how a signal path matrix is formed and controlled by the routing devices. It is important for operators to diagram their systems. This is performed by using basic symbols for microphones, wireless systems, line-level devices, mixing consoles, processors, power amplifiers, and loudspeakers. A system is easily documented once the signal path is discovered. Tracing a signal from the device's output to the next device's input is achievable by following the cables used to make the connection. Keep in mind, an audio system signal path is much like a road map. Cities are connected by roads, while devices are connected by cables. The direction of travel is output to input. In order to achieve the maximum sound quality coming through the audio system, it is imperative to set proper gain structure throughout the signal path. Gain structure is the setting of the voltage level as it is amplified at various points throughout the audio system signal path. These points are known as gain stages. This is achieved by establishing a unity gain. Unity is a term used to describe when the output signal level of a device is equal to the input signal level of that same device. This means as the signal passes through the device, it does not increase or decrease in level before reaching the output. Unity gain ensures the greatest dynamic range for the audio system. Dynamic range is the area between the weakest and strongest level that the device will produce without clipping or becoming inaudible. Headroom is the upper section of dynamic range between the nominal or average volume and clipping. Headroom allows the dynamics of the signal to pass without clipping the device. Signal-to-noise ratio is a measurement of the residual noise of a device, expressed as a ratio of the signal level and the noise level. Signal-to-noise ratio is important because if the output of a device is lower than its input level, the next device could increase noise, commonly detected as hiss. This would render a poor signal-to-noise ratio. Maintaining the proper dynamic range, headroom, and signal-to-noise of the system through proper gain structure is how we achieve quality sound reproduction through the signal path. Signal path, voltage level, and gain structure are vital elements in understanding the audio system as a whole. The signal path can travel from a single source to multiple destinations via a mixing console or digital signal processor. Keep in mind, an audio system is a chain of devices. Each link is vital to the function of the overall system. Setting proper gain structure between these links can eliminate noise, hum, and other audio anomalies from a system. When you understand basic signal flow as it travels from output to input, changes between acoustical and electrical signals, and the voltage levels used in the audio system, you will be ready to control multiple signal paths in an audio system with ease. The equalizer, or EQ, is the most common signal processor. Most mixing consoles and audio systems include equalizers. Equalizers consist of filters and frequency-specific amplifiers that boost or attenuate particular frequency bands. They are used to modify the tonal and timbral properties of an audio signal. An audio filter is a circuit that allows only certain bands of frequencies to pass through. Filters are different from equalizers in that they are passive and only attenuate the audio signal. Types of filters include peaking, shelving, high pass, low pass, and band pass. A common misconception about equalization is that it is solely used to correct tonal imbalances in the signal. Actually, the use of equalization in a live sound reinforcement setting is used mainly to compensate for room acoustics. Frequency